Yeah, they're a little discombobulated. Anytime, yeah.
Let's start.
Because I was thinking there was going to be coffee. Coffee for this.
Yeah, anytime.
Okay. Well, hello and welcome everyone. It's my great pleasure to introduce our speaker today, Dr. Amato Evan. And I was just informed that Amato is our first post-pandemic, out-of-town, in-person speaker. I think I maybe was the last out-of-town before the pandemic, so it's closing the circle here. Amato did his undergrad in Oregon State,
Yep.
and then came here to do a master's, then worked at Sage and Sims, and then did his PhD here. Worked with Dan Wymond and Ralph Bernards, and then went straight from here on to a faculty position at University of Virginia in Charlottesville. Spent about 3 years there. Then you moved on to Paris for a why not? For a year in Paris.
Yeah.
And then
You can swing it.
Yeah, and then a year, and then since 2012, I think, you've been in San Diego at Scripps Institution of Oceanography. And I joined there in 2013, that's where we first met. Amato is a leader in the field of dust, is that right? Especially African Saharan dust. You've worked with clouds quite a bit when you were here, and more recently also on snow. And I think that's what we'll hear mostly about today. Yep. So with that, a warm welcome. Thank you for coming.
Yeah. I'm psyched. Thanks for everybody for showing up. It's great to do this in person. I'm like zoomed out, as I was saying before, so like I wouldn't do it any other way. So I appreciate the opportunity to come here and that all of you are here as well, so we can share science in person, which is kind of the way to do it, I think. Anyway, before I get going, anybody in there, close to graduating, getting their PhD, there's a Scripps 2-year Scripps postdoctoral scholarship award, 2-year fully funded postdoc fellowship, and applications are due November 5th. If you're interested, you just search around, find some faculty that do something you want to do, and reach out to them and write it out. It's a pretty simple, like just a 2-page application. So if anyone's interested, and this is the Scripps Pier, this is the south side, and these are some south side shredders about to potentially get barreled. Anyway, because there's a beach there, so everybody serves at Scripps, so that's why I threw that out. So as Till was saying, I do a lot of work in dust, and so before I get into the snow stuff, I just want to do a brief digression here. Just to kind of say, this is actually the thing that I'm spending a lot of my time on right now. And so here's La Jolla, where Scripps is. In this red box here, this is the western edge of the Sonoran Desert. And inside that Sonoran Desert here, this is the Salton Basin, and this is the Salton Sea. Now this is a goes east animation. On this day, goes west wasn't working because it hardly ever does, it seems like, from January 29th, 2020. And as this animation goes, you can see like a dust storm coming off of the northern tip of the Salton Sea and moving over. I just chose this one because it's relatively straightforward to see the dust because of the contrast it makes with the dark water of the Salton Sea. I have a research site right here where this blue square is, and there's a collaborator of mine, Robert Frowan, where we have some instrumentation designed to study the radiometric and physical properties of dust and dust storms. So this is a permanent aeronet site. We have a LiDAR, some other radiometers to measure shortwave and longwave flux. And we go out there during dust storms and launch weather balloons to understand the structure of the atmosphere when these dust storms occur. If you notice, this balloon, this is the bottom of the balloon. It's not actually flying upward, it's flying sideways because we let this off into a dust storm where there was a really strong low-level jet, which was kind of interesting. And so I spent a lot of my time here, driving out there, cleaning dust off of stuff, occasionally doing science. And so, for example, one of the goals of being out there is to make really good estimates of the dust direct radiative effect. And one way that we're trying to do that is repurposing an instrument, for example, called a cloud droplet probe, taking that out into the field and make measurements. This is the dust size distribution. So on the vertical axis, this is the normalized dn, d natural log of d, where uppercase n is the size of the number concentration, and capital D here is the diameter of the particles. And trying to make size measurements way out here. It's kind of unique is that most size measurements kind of get clipped off right around here because of the way that optical particle sizers work, but this is an open path instrument if that means anything to you. All this is to say is we're measuring these really large dust particles, which we think are really important for understanding how dust affects the global climate. One of the other things that we're doing with some of the more meteorological measurements is looking at the dynamics of dust storms. What creates the high wind speeds events, and how does the dust interact with those high wind speed events? And so this was a case, and specifically that balloon that I showed, we launched kind of right here, and in a dust storm here that we determined was generated from a density current due to some evaporative cooling from upwind convection that was occurring, spillover precipitation, I should say, in the lee of these mountains where we are. So it's an interesting basin to study the dynamics. Anyway, we use the measurements that we're making to understand how dust is emitted, the cycles of dust emission, for example, in this density current, the structure of the density current as well, because dust in a way is a passive tracer for the circulation of this system. And so it makes for some pretty fun science. The other thing that's interesting is that Salton Sea here, it's drying up because of water management changes. It's actually an artificial sea anyway. It's a whole big long story, but it's drying up, and so it's interesting to look at what are the feedbacks on the boundary layer processes as you go from a closed basin that has a big, really large body of water that's quite shallow to not one at all. So you might say, well, what the heck does that have to do with snow? Well, on the surface, nothing at all. However, the one reason why I got kind of interested in snow is because as the world warms up, one thing that we're seeing in a lot of places is that there's more dust kind of emitted. Arid regions are getting a little more arid also as water stresses increase, as populations increase. And so dust deposition onto snowpack is a really big deal because it changes when snow melts across the West. And so that's my interest. But once I started digging into snow data, I found that, wow, there's a lot of other really interesting problems. And so this is one problem that I found that I'm sharing with you today. And really, the story about snow in the Mountain West, which is what this talk is about, you don't have to travel far to see what we think are probably the impacts of climate change on the mountain ecosystems. Okay, so here's a picture of a lake in the Western Sierras, and you might look at this picture and offhand think, oh wow, that's a nice fall day. It's actually not. It's the middle of summer. These are evergreen trees, and they're all dying. Right? And so why are they dying? They're dying because there's heat stress, there's dying because there's water stress, and then those two things put together, there's an invasive species called a bark beetle that's basically going through, and when trees are susceptible, they're able to destroy all these pine trees. So there are huge areas, for example, in northern Utah, where there's basically like a standing order that, hey, fire starts over here, let it go, because that's the only way they're going to get rid of this bark beetle infestation is just to let all the trees burn. And, if you were paying attention at all, I'm sure you had smoke here from all the fires we had in California this last summer. This is the Camp Fire in 2019. This was the deadliest fire in California history. About 150 people died, most of them when this fire rapidly overtook the town of Paradise, California. And this is a result, really, of drier ecosystems, a lot of fuel, a lot of dead trees, and long, warm summers. And so I really want to focus on that long, warm summer component of this. Now, it's going to take me a couple extra minutes to get into my what my research question is here. The first thing, before I can really tell you what the question is that I'm going to try to answer, I have to explain the data that I'm using. And so there is a whole network of sensors across the Mountain West called Snow Telemetry sites. And what a Snow Telemetry site is basically you take a nice little patch of forest, and inside this fenced area here, clear out a little space, there's a fenced area, and inside that fenced area you put a giant pillow made out of rubber, essentially, that's filled with antifreeze. And so as snow falls down onto this pillow, that antifreeze kind of runs through a little tube into the shack here, and you can measure the weight of the snow on that pillow. The weight of that snow is referred to as snow water equivalent. And it's just giving you an indication of the mass of snow that's falling at any one place. This data is really, really high quality because we're pretty good at measuring how much things weigh. That's a pretty easy measurement to make. And that data has a resolution of, I think, if you really needed it, like maybe 10-minute resolution. The data is transmitted in real time. You can see there's a met station right next to this one particular SNOTEL site, Virginia Lakes Ridge. And so it's kind of a great data set if you want to look at climate change. And I should mention, yeah, so Virginia Lakes Ridge, this is here in the Sierras. I think that would be close to Kings Canyon National Park, or potentially inside of it. All right, so that's what a SNOTEL site looks like. These are all the SNOTEL sites that I'm using. About 400 sites that have continuous data. So SNOTEL, this whole network started in the mid-1960s. But I'm looking at data specifically for 1981 through 2019. This is when you kind of find this really nice space where there's a lot of sites that have continuous data. Right now there's closer to like 800 sites, I think, that are operating. But I'm using these 400, and you can see they're placed all around the Mountain West. And the idea for these was to put these SNOTEL sites in catchment basins so that folks that need to know how much water there is running off into the reservoirs, how much water, what the water resources in the spring and summer are going to be. That was the rationale for where all of these stations were placed. Not necessarily to do climate science at all, but rather water management policy. So this is the kind of time series that you might get from a SNOTEL site. All right, and this is that Virginia Lakes Ridge site, and this is 2017. 2017 was like a great snow year, just tons and tons of snow. In fact, in the 9 years that I've lived in San Diego or in California, really, I think 2017 and one other year were the only years that weren't considered drought years in terms of how much precipitation fell, which gives you a little indication of why there were so many wildfires last summer. All right, so snow water equivalent, or I'm going to call it Snowpack, just like TPW measured in centimeters, or expressed in centimeters, I guess, typically. And so what you typically have in any one location in a mountainous area that gets, a sizable amount of snow is that the snowpack kind of gradually increases throughout the year and then rapidly melts in the summertime. Now, I should note that this is for the 2017 water year. And a water year is defined as October 1st of the previous year up until September 30th of that year. It's just a convenient way, most of the precipitation in the West falls during the winter, and so if you have to split up everything around January 1st, it's very inconvenient. So it's much better to look at these in terms of water year days. So in fact, water year day, this date when all the snow goes to zero, that's like around late June. So that's what I was saying. It was a really good snow year. The snow didn't melt until quite late in the year. All right, so the thing that I'm interested in, finally getting to the question here, all right, I'm going to call it zeta. And that's the day where all the snow melts. And I think of it as like, if you consider the seasons in the Mountain West to be like the snow season and the not snow season, this would be the end of the snow season. This would be when winter is over and when summer is really starting, okay? And let's just take that zeta. And let's assume the first order, zeta is a function of the annual mean temperature and the annual mean precipitation, which kind of makes sense. A year where it rains a lot or there's a lot of snow, the snow's going to melt later in the year. A year where it's really warm, the snow's going to melt earlier. So, or a year that it's anomalously cold, for example, the snow will melt later in the year also. Okay, so we can assume that this is a linear function here. Zeta is a linear function of temperature and precipitation. We'll just say that, all right, well, a change in zeta is due to partial zeta, partial is equal to partial zeta, partial T naught. And we'll call that term the sensitivity of the date of disappearance to temperature. So typically this is called the date of disappearance. I'm just going to call it zeta, the last day when there's snow on the ground, okay? So that's the sensitivity of that date of disappearance to annual mean temperature times delta T naught, and then we have the sensitivity to precipitation times delta P. Okay, so here's this expression for how a change in zeta, and we can solve for delta zeta, delta T naught, the sensitivity of the date of disappearance, or zeta to temperature, and annual mean temperature and annual mean precipitation for using multivariate linear regression. So we take a time series of, say for that one site, Virginia Lakes Ridge, we take a time series of zeta, we can take, comes directly from the observations, and then we can get a time series of T naught and P naught from the North American regional reanalysis, for example. So it's just annual mean temperature, annual mean precipitation. There are a couple of things we have to do. We have to think about lapse rates and how high the sites are, but those kind of details are relatively boring. But what's interesting is if you make a plot of partial zeta, partial T naught, there is quite a bit of spatial structure to that sensitivity. And so the question, finally, 10 minutes into the talk, the question is, why? What causes this spatial structure? One might assume that, if the temperature increases, the snow melts a couple days earlier in the year everywhere, why should that be a function of where you are on planet Earth? And so let me just run through this. For example, we see the smallest magnitude sensitivities in the Wasatch, in the Rockies, in the Colorado Rockies. In these places, for 1 degree of warming, okay, according to this multivariate linear regression, for 1 degree of warming, snow melts 0 to 5 days earlier in the year. So I would say these are areas that don't seem to have much sensitivity to increasing temperature in terms of how long there's snow on the ground into the spring and summer season. Whereas if we look out into the Cascades, the Sierras, and then down here, like Mount Lemmon and southern New Mexico, we see sensitivities that are even as high as negative 30 days per degree Celsius, meaning for the same amount of warming, over here in the Cascades, winter ends, all that snow melts a full month earlier, according to the observations. So it's not clear to me, when I first saw this, why that would be the case. Okay, so you can approach this problem as, and I don't mean to be derogatory, but as a hydrologist, where it's going to be very complicated, and I'll talk about what that might mean, but I prefer to approach these kinds of problems more as a climate scientist, which is what I learned to do here, right? And so as an analogy, let's say that we have a really nice 1962 Corvette. We want to know what makes it work. What makes this Corvette go, all right? So you could get into the engine and you could be really complicated and try to figure out, okay, what's going on here? What are the brakes? There are all these components. Does the color matter of the car? Does the steering? There's just like a lot going on in a car, all right? But I think the way maybe a climate dynamicist might think about it is say, well, let's just boil this car down to an idealized model of a car, all right? All right, I've got like the wood thing here, and I've got some wheels. And you say, oh, in my idealized model, the car moves because it has wheels. The wheels go roundy-roundy. They're attached to the axle, and the body of the car sits on the axle, and it doesn't go round, and it stays stationary with respect to the axle. Oh, okay. That must be how a car works. And then what you do is you increase the complexity of your model to still see, do my original findings still hold? And indeed, you get a Matchbox car, and it has different colors, and it's slightly more complicated, but still it rolls and goes because you have the wheels on the axles. And you can keep going even up further in complexity. Maybe you have a go-kart and you put an engine there. But all of these vehicles are still going because they have the wheels. The frame of the engine's attached to the wheels, and that's how it goes. So a hydrologist might think of this problem, and they say, well, if you want to know what's happening with snow, you need to really understand the surface heat budget and the surface water budget, okay? So we need to keep track of shortwave radiation, what that's doing. We need to think about shortwave radiation that's making it through the canopy. What kind of surface we have? Do we have a dense forest? What's the forest cover? What kind of canopy is it? Are we looking at a grassland? Is it really rocky? What are the types of soil? How does that change the ground heat flux, the flux of energy from the snowpack down into the ground, or vice versa? We need to think about outgoing long-wave radiation. How tall are these trees? They're intercepting snow. Is that snow drifting down onto the snowpack? We need to think about wind and sensible and latent heating. Wow, that's a lot of stuff, and it's going to be really hard to figure out anything if you have to keep track of all of those different components of the problem. So as a climate dynamicist, I think, well, let's make an idealized model of snowpack. Let's say when it's cold, it's snowing, and when it's warm, the snow is melting. Happening. It's a sad skier there. I kind of like that picture. All right. So the idealized model of snowpack maybe is slightly more complicated, but that's the basic idea. I'm going to put together an idealized model of snowpack, see if that explains those observations, and then maybe increase the complexity of that model to see when it starts to break down. All right, so my idealized model of snowpack. Temperature was the most important thing, so I have to have some way of representing temperature. And I know this is a little hard to see. Well, you can't really see the shading a little bit, but so let's just say anywhere at any of these SNOTEL stations, the temperature follows a sinusoidal pattern, all right? So we can describe that daily mean temperature as T0, the annual mean temperature, minus T1, the amplitude of the annual cycle of temperature times sine omega t, where omega is just 2 pi over 365 days, lowercase t is time, and then minus some phase offsets, just a sine wave, okay? This dashed line right here represents T0 for this case. And this happens to be, I think, this would be an approximation of the annual cycle of temperature at that Virginia Lakes Ridge site for 2017. All right? So now let's say that snow can accumulate when the temperature is below some temperature, we'll call that the melting temperature, and snow will melt when temperature is above some temperature called the melting temperature. We can make that 0. You know, we can say, well, snow accumulates if the temperature is below 0 and it melts if the temperature is above 0, but then that's not, you know, we can be a little more sophisticated with that without making our model too complicated. And that's because, you know, that really isn't the way that it works, especially if you have an area where there might be shading from vegetation. Snow doesn't really melt. And plus, this temperature, this is the air temperature. It's not the temperature of the snowpack. And the temperature of the snowpack is the thing that determines if you have melting or not. All right. So, oh, and that's that TM. All right, so now we need to solve our idealized model. We need to know how much time we're spending below, how much time we are in a regime where the temperature is below the melting temperature and how much time we're above the melting temperature. And so it's relatively straightforward to solve, and we get this arcsine function. So T, lowercase t subscript d, that's the time, or the water year day, when the temperature drops below the melting temperature. And that's the arcsine of this T0 minus Tm divided by T1. And then the time when the temperature rises back above Tm, it's just similar, but negative with the half of a sine wave there, half the wavelength. Okay, now, we're going to have a really simplistic model of precipitation as well. We're going to say that precipitation basically follows a step function. We have, you know, precipitation is on and at some water year day it turns off, which is kind of how it works a little bit. We get all of our precipitation in the west, like during the winter and the spring season. So let's just say that for right now. Eventually, we're going to take a partial derivative with respect to temperature, and precipitation is going to fall out anyway, so it's not really that big of a deal. All right. And then the next thing we need to do is we need to know the rate at which snow accumulates and the rate at which snow melts. And so we can just go back to like these SNOTEL, these snow water equivalent curves. And we can just look at, well, from the time when the ground first gets covered with snow till you reach the peak, that's the accumulation rate. And this is the melt rate. The melt rate's always a lot steeper. And both of these positive definite, the melt rate is always a lot steeper because the melt rate is very strongly a function of solar insolation. And so if you have a place, especially with a lot of snow, and the snow doesn't really start to melt until June, when the sun is high, the solar insolation drives really, really steep melt rates. Okay? Now, we can put these things together, and we'll say, all right, now snow is going to accumulate at the rate Ra when the temperature, when time is greater than T down and it's less than Tp. All right? So as long as the temperature is below the melting rate and it's snowing, snow is going to accumulate at some constant rate Ra. And similarly, we're going to say snow is melting, Rm, when time is greater than T up and it's less than zeta, all right? So here we have zeta here. And so we get the melting equals Rm and then T minus Tm. Okay, so this is how much melting is occurring, this is how much accumulation is occurring. All right. Just as a quick aside here, we can estimate snowpack as just the accumulation minus the melting. We have to kind of be conscientious about what's happening here over at the edges. It's, you know, the value is going to be 0 if time is less than T down or greater than zeta. Snowpack is 0s. But I only want to point this out just to show what this idealized model looks like, idealized model of snowpack compared to some observations. Obviously, I cherry-picked a really nice case. This doesn't always work so nicely, but just so you get a feel for the simplifications that we're making. Here's from the idealized model. Here is temperature from 2017 from that Virginia Lakes Ridge SNOTEL site. You can see, okay, yeah, kind of gets the basic stuff there. If you added a second sine wave, it would look a little nicer, but whatever. You can see precipitation kind of goes and then it falls off. Yeah, more or less. Not a terrible approximation. You can see that the resulting accumulation and melting rate, and granted, for this example, I picked a precipitation, the date when the precipitation stops, just to make everything look nice. This is a little arbitrary on my part. But anyway, and then you look at the snow accumulation and the snow melting from SNOTEL. Okay, we're capturing kind of at least some of the most basic features here, and then this is our resulting curve of snow water equivalent and how it compares to observations. I've smoothed the observations a little bit just to make things look a little nicer, all right? So it's not bad. And if we do this for all of these sites and we maybe make an annual average, if we were to remake this kind of plot, but for all the SNOTEL sites averaged together, it would look something similar to that. You know, there are places where this model starts to break down. Maybe temperature is doing something a little funny, or maybe, you know, we get a lot of snow in the beginning of the year and the snow melts really early. Okay, so we're not going to capture that. But by and large, this is the way that the seasonal cycle of snow looks. All right, so back to the thing that we really care about here, which is that zeta term. We can define the total snow accumulation as essentially just the rate at which snow accumulates times the number of days that the temperature is cold enough for snow to accumulate. We can define the total snow melting as the rate at which snow melts times the number of days that, the days between T up when snow starts to melt and the day at which zeta, when all the snow has melted. And so if we make the assumption that the surface is snow-free at some point in the year, so we're in a location where there's snow on the surface for some point in the year and then it's not snow-covered for some duration, right? We just equate the total snow that's melted to the total snow that's accumulated, and we can rearrange and find an expression, an analytical expression for zeta. So you have to remember now, this T down and T up, these, the expressions for T down and T up, those were those arc signs that had arc sign of T naught minus Tm divided by T1, okay? So we want to take the partial derivative of zeta with respect to annual mean temperature. And because of those arc signs, that's where we get kind of this funny thing happening right here, okay? So where partial zeta, partial T naught is equal to negative 1 divided by omega times the square root of T1 squared minus the difference between T naught and Tm, the annual mean temperature and the melting temperature squared, times 1 plus the ratio of the accumulation to the melt rate. All right, so the whole point of doing this idealized model is we end up something that we can understand. We end up with something that we can understand, we can make sense of. So to kind of dig into this a little bit, let's just assume that the melting temperature is 0 degrees Celsius, just because it makes it a little easier for me to wrap my head around it, all right? So then what do we get here? All right, so in our expression for the sensitivity of zeta to annual mean temperature, we find a solution. Since RA and RM are always positive, we get a solution that is always negative, meaning that if temperature goes up, the date at which snow melts has to go down. All right, snow melts earlier in the year, which makes sense. Our solution then gets larger as T naught and T1 get closer together. In other words, the closer that, our solution gets smaller the closer these two get together. So in other words, if we have an area where the annual mean temperature is close to 0 degrees Celsius, but the larger they get, all right, the larger the argument of this square root term, okay, the smaller our sensitivity. So what does that mean? If we're in an area where the annual mean temperature is close to 0 degrees and there's a large seasonal cycle, okay, then we have very small sensitivities, all right? And so think back to that picture of the Colorado Rockies, right? This is an area high up in the mountains where you have probably snow for 6-7 months of the year. The annual mean temperature isn't too far from 0, but you have warm summers and you can have very cold winters, all right? So you have a large amplitude of the annual cycle and a small temperature. Dan?
So T naught is the annual mean, it's not the temperature at which, okay, Tm is your melting.
Yeah, melting temperature is Tm, T naught, yeah. And so here I'm just assume the melting temperature is 0 just to make it a little easier, okay. And so then what this expression also says then is that as these two get closer together, as the annual mean temperature is closer to the amplitude of the annual cycle, this sensitivity starts to grow. So if you think, you know, we had these large sensitivities along the Pacific coast, well, here we're at a place where the temperature is warm, the annual mean temperature is a little bit warmer, it's kind of modulated, and the amplitude of the seasonal cycle is small because of the proximity to the ocean, right? And so that's what this expression would tell us, well, that's what's happening with those high sensitivities. I should mention here as well, oh, and then we're undefined if T naught is larger than T1, but that just means that it's undefined if we're in an area where the temperature never goes above the freezing temperature or never goes below. If we're in an area where it's always snow-free or it's always snow-covered. So we would be undefined on the Greenland ice sheet, okay? And we would be undefined in Mexico. All right, the ratio RA to RM, it's kind of stable, it's kind of boring, doesn't really change that much from one place to the next, and I'm not even sure why, it's usually around 0.3. So the real variability that's coming from that plot is all having to do with this term 1 divided by the square root of T1 squared minus T0 squared. Okay, so let's go back to this, the expression that has the Tm in here. So we determined this sensitivity using observations, all right? So we can go back and we can make this calculation. We can calculate what this sensitivity should be according to the theory here that we've developed from our toy model, where we can estimate T0 and T1 directly from reanalysis data. We can estimate RA and RM directly from the SNOTEL data, and a long-term mean value for all of these. And then we can estimate Tm, looking also at a combination of the SNOTEL data and reanalysis data from temperature, just defined in this case as the coldest temperature at which snow melts. All right. And so if we do that and compare to the observations, we see that the idealized model does quite a nice job reproducing the spatial structure of the observed sensitivities, which implies then that we're kind of on the right track. Well, at least it's consistent. Our theoretical framework is consistent. So we see, again, these large magnitude sensitivities along the coast. Now what's happening down here as well, this is an area where, although the annual cycle is really large, the annual mean temperature is also quite large. So the magnitude, the difference between the magnitudes of T0 and T1 are small. And then, you know, we're more in the interior of the continent. Temperatures are cold, annual mean temperatures are cold, but the amplitude of the annual cycles are quite large, all right? So, and if we were to put these on a scatter plot, the correlation would be like 0.6 something, for sure statistically significant. Of course, there's a lot of autocorrelation in the data as well. But if we kind of go back to this expression, maybe another way of thinking about it is just, you know, to parse that out between, let's say, a warm coastal region and an interior region, okay? So what this expression is telling us, and this is where we're trying to gain the physical insight from the idealized model that we created, is that when, and let's just say temperature, for this case, snow melts when the temperature is below 0 degrees Celsius, okay? So in this case, on a warm coastal region, the temperature, the 0C isotherm, passes near the flat trough of the sinusoid, describing the annual cycle of temperature. And in this case, if we have a 1 degree change in temperature, right, we have a very large change in the number of days that snow is allowed to accumulate. You almost have to think in arcsine space, right? So instead of thinking about the amplitude of the annual cycle here as a function of day, you think about the days as a function of where you are in the amplitude of the annual cycle, okay? So how many days are we below 0? Well, or how many days are we below 0? Right. If we just increase the temperature a lot, we're going to make a huge change because we're most sensitive. The sinusoid is very, very flat right there. So there's a large change in the number of days for a small change in the annual mean temperature. Whereas if we go to an interior region, so a cool region with a large annual cycle, we can say, all right, well, let's say we have a temperature, the annual mean temperature is 0 degrees Celsius, right? And so now since we're passing through the steepest part of the sinusoid, a small change in temperature has a relatively small change in the number of days that the temperature is below 0, and vice versa for the temperature above 0. So in the first case, a 1 degree change in temperature resulted in snow accumulating for about 24 days less, and it took, you know, about a week less for that snow to melt, whereas for the same amount of warming in an interior region, right, the snow accumulates for only 6 days less, for the same amount of warming, and it melts just over 1 day less. So for the upper case, right, 1 degree change in temperature results in snow melting 20 days earlier in the year, whereas for the cooler case, the snow melts only 5 days earlier in the year. And that would be kind of the physical understanding, I think, that we would get from this. So that's with the toy model. We can increase the complexity. We can go from like the little wooden car to the matchbox maybe, all right? So to do that, we're going to use the Variable Infiltration Capacity of VIC model. This is a full-on hydrological model that simulates all of these important processes. So we'll take that model and force it with long-term mean meteorological variables from the North American regional reanalysis, and I think I put reanalysis twice there, interpolated to each of those SNOTEL sites. Great.
Wouldn't you expect that global change, global warming, would affect the minimum temperature more than it would affect the maximum summertime temperature, so that it would change the shape of the sinusoidal curve rather than just moving the mean up and down?
Yeah, that's a fair question. I'm trying to remember if I explicitly looked at that, but yeah, in other words, the shape of the annual cycle of temperature might be changing some.
That's what I would think, because I think, the carbon dioxide effect or global warming would affect the minimums more than it would affect the maximums, I would think. Maybe that's not true. I guess I'm not an expert on it. I don't know.
That's a good question. I haven't looked. I remember looking at how those changes as a function, and I was just pulling up a plot looking at how the changes were as a function of season. It's earlier, and there is some seasonality, but it wasn't. I have to go back and look. If afterwards, or I can go. I don't think I have it in here, but I do have a plot where I looked at the seasonality of those changes, and certainly, yeah, that definitely has an impact. And insofar as that the seasonal cycle doesn't. There is another thing too, where this model breaks down, and that is these terms right here. The rate of snow accumulation and melting, these also change as the climate warms. And specifically, this one actually gets, the snow melts at a slower rate as the planet warms up, and it just has to do with the fact that when snow starts melting, as the planet warms up, snow melts earlier in the year when the sun is lower in the sky. So there's not so much solar insolation to drive these really fast melting rates. So, also, not correct, strictly speaking. But yeah, I can go pull up that plot because I did specifically look at that. I should mention too that I did this with using reanalysis. All of these SNOTEL sites have met stations, but they don't have really good quality data until around close to 2000. So using actual measurements from the SNOTEL sites, able to reproduce the same thing. So just to make a quick note of that. All right. So we ran this model and calculated partial zeta, partial T0 directly from the model output, and then via that analytical solution to the idealized model, that expression, all right? And so if we plot these two things side by side, you see that, right? So this is partial zeta, partial T0. So again, ran the VIC model for all those sites and just kind of increased temperature and decreased temperature, so we got a range of 1 degree Celsius, and calculated the change in zeta. How much earlier in the year snow melts for an increase in temperature, okay? So this is directly from the model output, just saying this is when the snow melts in the model. And then we did this, sorry, it says equation 2 here, but it's really that theoretical expression for partial zeta, partial T0. So just using the temperature and the rate of accumulation. So the metrics describing the annual cycle of temperature and the rate at which snow melts and accumulates. And we were able to pretty much explain all of the variability in the VIC model, which I think is good. It suggests then that even in a more complex model, even though we have all of these other processes like, sensible heating, latent heating, and we have, water fluxes and heat going down into the surface and vegetation types. And in fact, you can get something pretty similar. I think I did this just for like a 50% forest cover. We could make it 100%, we could make it a grassland, still get an answer that's pretty consistent. So with a little bit of confidence that this idealized model tells us something useful about how zeta, or how the date of disappearance is changing for a warming planet, I'm going to estimate T0 and T1 globally using the output from the MIRA 2 reanalysis. And then we can just assume constant values of the rate of melting, accumulation, and the temperature at which snow melts, all right? So if we do that, and we look at, for example, the northern hemisphere, we get a map that looks like this, all right? So we have sensitivities that are small in magnitude in the interior of North America, northern North America, and Eurasia, for example. So sensitivities that are on the order of 0 to 5 days per degree temperature of warming. So these are areas then maybe where the amount of time that I shouldn't say the amount of time, when the snow melts is not super sensitive to a unit increase in temperature. And then we find all these areas where there is a very large magnitude sensitivity. And some of the places that really stand out to me, for example, are the European Alps, where it's long documented, receding glaciers and the impact of warming on the cryosphere in this area. And really just the Rockies as well, and then just all of these areas where, except for when we get into the Himalayas, there's more of a sharp contrast, okay? So all these areas around the southernmost latitudes where snow is on the ground for some period in the year, these are the ones that are most sensitive to warming. But interestingly, we also see these large sensitivities in the Arctic, coastal regions in the Arctic. Northern Alaska, the Scandinavia along the coast, all the way up into the coastal Alaska as well. Iceland, coast of Greenland, okay? And really, one thing that I didn't mention is that this solution is actually symmetric about T naught. So it doesn't matter if the annual mean temperature is positive or negative. The sensitivity is only the difference between the magnitude of the annual cycle and the difference between the amplitude, the magnitude of the annual mean temperature. Well, seasonal cycle amplitude is always positive, so that doesn't even matter. But anyway, so let's go back to this example, all right? So we had a warm coastal region, an interior region, and let's look at a cold coastal region, okay? So let's say like Iceland, okay? So we can have a region where the annual mean temperature is -4 degrees Celsius, all right? But the amplitude of the seasonal cycle is quite small. And it's the exact same rationale. Now, we are, instead of the annual mean temperature passing near the flat trough of the sinusoid, it passes near the crest of the sinusoid. And so it's the same kind of thing. A 1 degree change in temperature results in a large change in the number of days where the temperature is below 0. And so for this case, which obviously I chose to kind of bring out the symmetry in our expression for that sensitivity, we can see that both in a warm coastal region or in a cold coastal region, we can have the same sensitivity, -20 days per degree Celsius, to a 1 degree increase in temperature. And so what that suggests then is that the regions that are most sensitive to warming as far as snowpack on the ground goes are also, or I guess I should say, the regions that are already most marginal. Okay, so you think about the Pacific Northwest, somewhere that's already on the limit, okay? You think about the Arctic, all right, already on the limit, right, in terms of like being snow-covered all year or not snow-covered for part of the year. These kind of places that are already marginal are the ones that are the most sensitive to future change. Whereas it's these interior areas that already have long snow seasons, they're the most buffered. So it's almost like the places where you don't want global warming to be, impacts to be the strongest are indeed the places where the impact of global warming looks to be the strongest. So, just to summarize, key findings. Okay, so this is a paper we published this year in Nature Climate Change. Change in snowpack disappearance date per unit warming is not uniform. It's a function of a location's mean temperature. And we developed an idealized model that solved for zeta and used it to explain the underlying physics governing the behavior of partial zeta, partial T naught. From the model, zeta is most sensitive to warming in regions where the annual mean temperature is well above or well below the melting point, and where the magnitude of the amplitude of the seasonal cycle is quite small. And then we use this idealized model to examine the sensitivity of partial zeta, partial T naught globally, finding the largest sensitivities at low latitudes and near the poles. And I guess I should say, since I have just a couple minutes, I just want to throw out one slide, 2 more slides here. And that is, if you could talk to someone that really spends a lot of time worrying about hydrology in the Mountain West, they might tell you, okay, yeah, that means something, and probably ecologists care a little bit more about this metric than maybe somebody that's worried about how full their reservoirs are going to be. People that worry about reservoirs and water capacity and water storage, they think about April 1 snow water equivalent. And there are negative trends. So these circles are representing areas where people have been making snow course measurements since 1955. It's like somebody trips up April 1st, stick a tube down in the ground, they pull up the snow, they weigh it, and they're like, oh, that's how much snow there is. And people have been doing that in locations around the West since the beginning of the 20th century. All right, and so it's really hard to find trends in snow because precipitation is so variable. Or it's really hard just to look at, oh, there's, So what they do is we plot, well, these are areas where the trends are negative. So there are downward trends in snow water equivalent. Most of these are not statistically significant, but then people try to say, well, it's important because they're all negative. Okay, whatever. But one thing interesting about that is that if we look at the sensitivity of April 1 snow water equivalent to annual mean temperature from SNOTEL, we see this negative, this sensitivity to annual mean temperature. In other words, similar to looking at the date at which snow melts, the actual amount of snowfall, the actual snowpack on April 1st, and the sensitivity of that snowpack to continued warming also seems to be a function of the annual mean temperature. And this is from observations, and I pointed out that the black dots all represent the Pacific Northwest, and I just pointed that out because probably nobody here cares about it, but it's just because people will try to make an argument that that's like kind of a different regime because you get late season, because there's so much precipitation after the temperature is warmed up. Anyway, and also like in these VIX simulations, able to take that same set of simulations and look at the sensitivity. And so I think there's more to do looking at toy models and snowpack and how snowpack is affected by climate change. This problem ends up being a little bit more tricky in terms of finding an analytical solution to the snowpack on April 1st, so haven't really delved into that too much. But anyway, that's all. Thanks.
Couple of questions, I guess. First of all, it's really fun to see this, and I take strong objection to you claiming that climate scientists just approximate everything as a simple toy. But you've done a very good job with that. So, have you looked at receding versus advancing glaciers and records of that to see whether or not they're match up with some of these marginal areas?
Yeah, you would expect to see kind of a similar dependency of the sensitivities then.
It'd be interesting to see if there's...
Yeah, no, I have not, and I have to say I've struggled to find an equivalent data set other places, right? So I took this model and I developed it with data over the Western US and extrapolated it globally. It's been really tricky to find, some other global records that are, because it's a very specific thing, right? The day at which the ground becomes snow-free. You can't use MODIS, for example, right? There are all kinds of, most satellite products give you like a weekly estimate, right? Of how, if the ground is covered with snow or not, for example. And so it's a very specific thing. You need that resolution on a daily time scale, otherwise you're not gonna see the signal. Yeah, that's a good idea. I didn't even think about looking at glacial records though.
Yeah, I'm not sure. Maybe Phil have more to say on that because it's a different accumulation and transport. So I'm not sure if it'd be useful or not. But the other question I had was your model is premised on the idea that you have a certain accumulation that shuts off at some date. And how does that date relate to the crossing point of the zero line? Is that
right? It shuts off just on the day when I say it has to.
Yeah.
Yeah. And arbitrarily chosen, somewhat arbitrarily chosen, right? So I just say, like, snow can accumulate if the temperature's cold and then, like, up to here. In reality, I could just say it accumulates the whole time the temperature is below zero, and I would get it. And specifically for this problem, because I'm taking, the precipitation just falls out of the expression for zeta, which is awesome. For that other problem, we're looking at the snowpack on April 1st, it does not fall out, and then you have to keep track of, well, what if I say precipitation ends here, or if it ends there? So then the problem becomes a bit more tricky. Yeah.
It seems like it would be very sensitive to that, given that what you're seeing there with the change in temperature is where the slope of your sine wave is weak. You have these large changes in that accumulation duration, and if that's the accumulation is sensitive to that. But
yeah, one thing I can say though is that at least, so the model is not perfect, obviously, but the kind of thing that makes me feel a little bit good is that the model actually underestimates the magnitude of the sensitivity. So, I'd rather underestimate than overestimate, but yeah. And I think the reason why is just, again, when you get into these places, the model starts to break down. The temperature doesn't follow a seasonal sine wave perfectly, get maybe late season precipitation that falls as rain. on top of the snow. So the model definitely starts to break down. Great, or anything?
Yeah, one of the things we looked at once upon a time, back when I was at CSU, was the sensitivity of the southwest monsoon to snowpack. And we found that years with light snowpack, the southwest monsoon was much stronger, so there's a reaction in the summertime to bring more precipitation. I guess there's no way you can take that into account with this. I don't, maybe there is, I don't know, but.
Yeah. Right, well, you know what, that actually brings up, you know, if I go way back here, one of the initial assumptions in the model. And because I think what you're really talking about there is an interaction between temperature and precipitation.
Yes.
To some degree,
Well,
right?
that's what a monsoon is.
Right, yeah, and so and so when I even formulated what this whole thing from the very beginning, I made this assumption that's not really true, that temperature is independent of precipitation. So, you know, if I wanted to be able to kind of dig into something like that, I think you'd have to have like some second interaction term here between temperature and precipitation to really dig into that.
Yeah, this was fun. I had two thoughts of completely different things. One was about trees, 'cause I like to think about trees.
Oh, yeah.
And insulation.
That's right.
And just trying to figure out, so snow-tell sites are usually open spots or exposed because they need to be able to accumulate snow. So that temperature measurement that you're using is also from that same location, is that correct?
I did it both ways. So I used, right, so here's a snow-tell site, it's a pretty forested area. I used reanalysis data for temperature, for my temperatures. And, you know, doing, like, trying to estimate some kind of lapse rate to take into account the fact that these sites, you know, are generally, usually, almost always at a higher elevation than like a, you know, 50 by 50 kilometer grid solids. But then I also did it a second time using the actual temperature measurements from the SNOTEL site, just to make sure they kind of got the same answer. But what specifically were you
Well, I was
thinking
just
about
thinking
this?
about, because you mentioned tree mortality and bark beetles, right? To what extent is a snowmelt temperature sensitivity sensitive to the amount of insulation hitting the ground as a function of vegetation above it? I didn't know if you've seen anything in your model stand out between more exposed locations at high altitude versus forested locations.
You know, I didn't. That is a nice thing to look at, because I can think of it too. Right. So I only ran model simulations where like everything was forested or nothing was forested, right? Just to make sure that the sensitivity is still kind of, you know, everything kind of balanced out. But I don't think I ever compared the sensitivities for those two different kinds, and that would be something nice to look at. Yeah. And the other thing too would be, you know, I'm assuming some kind of steady state, right? If you add in some kind of succession there, right, from forested to not forested, that would also be a pretty big thing. But yeah, that would be interesting to look at. You know, the other big thing too that I ignored was, like, for all these sites, they all have different slope aspects, right? They all are, you know, is the site facing a little bit north? Is it facing more south? Am I in a rain shadow? I mean, probably, you know, the next order of complexity you might want to add in is some kind of metric that describes, you know, you'd almost have to look at like catchment basin by catchment basin and some other kind of metric that describes, you know, vegetation and you know, if you're on the windward side or the lee side of a mountain, for example, or at least the slope aspect in elevation.
Yeah, you can make the problem complicated, that's you said.
Yeah, for sure.
Now the other one was to bring it full circle to your study on dust, because of course the other thing that folks in the West I remember talking about is these large-scale dust transport events leading to early snowmelt from black carbon deposition. I don't know if you've thought about that or to what extent that's still something that's kind of thought of as a major contributor to snowmelt.
It certainly is. I think about it all the time. And specifically, you know, I mean, just 2 days ago, we had an epic dust storm all across the entire state of California. And that dust was absolutely transported up towards northern Arizona, going into southern Utah, and then heading into, and the place where people think a lot about this in the San Juan, southern Colorado. And of course, the day before that happened, the battery for the sun photometer cracked, and the fan on this LiDAR basically shut off, and it got totally contaminated with dust, so I didn't get any of those measurements. But nevertheless, I think about it all the time. I've had a student who put together a climatology of dust based on using MODIS data over the western US and trying to start to look at relationships between melting rates and how much dust there is in the atmosphere. It's a really tricky thing to measure how much dust there is over land. Not so easy to do. Maybe with GOES West, maybe it's possible to do that with GOES West, but that's a huge thing. People think about it all the time, and especially, you know, as places like this get drier and as, you know, water bodies go away and, you know, God forbid this drought keeps going on for more years, I mean, it's definitely what's happening. There's already an upward trend in the amount of dust that's been measured in the western US, and so there's every reason to think that that'll continue to happen, and that's kind of what I'm hoping to go into. Just want to kind of try to understand the physics and do it right, but yeah. Yeah.
So to follow up on that, so are you saying that the addition of dust, say like in the southern Colorado Rockies, would increase the sensitivity to the temperature because it would enhance melting, or is it just like a nonlinear effect that your model wouldn't capture? Like, how do you anticipate it fit into your model?
Yeah, I mean, right, well, to the extent that temperature is increasing at the same time that dust is increasing, yeah. Deposition of dust onto snow causes snow to melt earlier in the year. So if the snow is happening in the spring, then yes, the snow would be melting. If the dust is happening in the spring, if you're having dust deposition on these white surfaces and you're getting the absorption of solar radiation, you start melting the snow. Right, yeah, then I would expect that those sensitivities would be specifically higher there. That might actually be something worth looking at too. For all of this data, I was looking at the melt rate and the accumulation rate as just something that was constant in time. And so, one thing that I'm hoping that Ian and I will continue to do is look at some of these other parameters. I just looked at one thing. This was like the date of snowpack disappearance. But you can look at, and in fact I've made maps of like the melt rate and the sensitivity of the rate at which snow melts to temperature, and trying to look at maps and understanding what's controlling that, because it actually does vary a lot from one place to another. So that might be the best way to do it too, to look at that problem from like kind of, you know, a satellite view, is get satellite data of dust and start to look at these melt rates and see from one year to the next if those melt rates, changes in those melt rates are correlated with the amount of dust that's around. The problem with the dust on the snowpack stuff is that it's really only been approached from a field site mechanism, meaning that, you know, people go and they have a bunch of instruments and they're measuring the albedo of the snow, they're measuring, you know, the amount of aerosols in the air, and you know something really well for this one place. But it's really hard to extrapolate that out. And so, I mean, thanks for the idea. Yeah.
One last quick question. So you have the sensitivity now. Can you use it to project forward? Like, what is the snowpack evolution going to look like if you take, you know, temperature output from GCMs and can you apply the model to that? I'm just thinking sort of, for example, polar amplification would mean that you have higher changes in temperature in the Arctic, so the Arctic with a higher sensitivity would like be doubly screwed,
Yeah.
whereas comparatively the lower latitudes might not see as much of a change because temperatures are lower.
That's a really good idea. Yeah. You know, it's just, you have to be careful. Again, the model breaks down. If a place starts to get kind of into that snow-free regime, snow-free all year round, okay, the model's totally broken down. It doesn't work anymore. But that's a really good idea, as we were talking about earlier. You know, in a GCM, I think I don't know exactly the parameterizations for snowfall in a GCM, but what I do know is that these are coarse grid cell things, right? And snow really happens on steep mountains that aren't represented. And so I know that most folks that use GCMs to look at snow, they take a GCM output and then they force it that VIC model with the GCM output to kind of see what's happening in a montane region. So I suspect there would be some subtleties there, because the atmospheric lapse rate, you know, you'd have like temperature at some, you'd have to kind of figure out the right way to figure out the atmospheric lapse rate, and kind of like Greg was alluding to as well, like how temperature might not always be changing the same way in every season. But